I'll be talking about the apparatus. First of all, we are going to use this device, this heat exchanger service module. So we'll be talking about the concentrate tube heat exchanger. First, as you can see, there's two tubes here, and this part, this is hot water system, and this is the cold water system. So we are going to use this apparatus.
Okey, dalam lab ni ada dua jenis eksperimen, iaitu counter flow dan parallel flow. Okey, untuk eksperimen yang pertama, kita buat counter flow. Okey, macam mana kita nak tahu counter flow? Dekat table ni dia ada tunjuk diagram di mana kalau counter flow untuk hole yang atas dia perlukan cold out, iaitu air sejuk keluar. Okey, dekat sini dia tulis cold return. So dia benda yang sama, cold return sama dengan cold out. Jadi lubang yang atas ni dia kata cold out TC2. Jadi kita tengok betul tak wire ni cold out. Okey, dia tunjuk sini tube yang ni cold return. Jadi betul kedudukan tube ni. Okey, kita check pula wire dia. Wire yang warna hijau ni. Tengok. So kedudukan wire ni betul, dia berada di TC2. Okey, kita tengok tube yang belah bawah pula. Dia kata kat sini untuk counter flow, dia kata call in TC1. Jadi kita check tube dia. Okey, dia tulis kat sini cold supply. Okey. Untuk cold supply, wire dia kena TC1. Jadi kita check. Okey, TC1 betul. Jadi ini adalah untuk counter flow. Okey, untuk parallel flow, kita hanya swap ataupun tukar kedudukan tube ni saja. Untuk parallel flow, lubang yang di atas dia perlukan cold in TC1. Jadi yang cold out ni dia pindah ke bawah, dan yang cold in ni dia pindah ke atas. Itu je. Terima kasih.
First, kita nak buat eksperimen ni kan, kita onkan dua-dua hose. Ini satu, yang ini satu. Okey, lepas kita dah on tu, make sure kita akan pump ni on, dan kita punya thermometer. Make sure dia kosong tau, sebab kalau dia keluar, dia punya temperature dia tak akan rise. Jadi kita mula-mula kita kena tunggu dia punya temperature jadi 60 degree Celsius. So sekarang kita buat counter flow. Jadi dia punya terminal dia macam ni, 7 sampai 60. Okay, once the thermometer is 60 degree, then we should open the cold supply till 3, the air flow. Same goes to the hot water flow till 3. Check if the water flow, there's water coming up, there's water coming up, so that means the water is running. So we take the data from TH1, TH2, TH3, TC1, TC2 and TC3. Then you just adjust the cold flow to proceed to the next step. And that's all. Thank you.
Hello, my name is PATERUS, and for discussion number 1, it asks us to create a simple temperature profile chart for each flow using the input and output temperature TH1, TH2, TC1, TC2 to sketch for both parallel flow and counter flow. So we did it. As we can see here, the chart for parallel flow and counter flow. For question 2, it asks us to create a chart of energy balance coefficient for vertical axis against heater temperature for the horizontal axis. So using the data or the result that we have taken from the experiment, so we plot a graph for parallel flow and counter flow. This is for parallel flow. As we can see, the energy balance coefficient start at 60 and the highest is around higher than 140. And same for parallel flow C. The next is for counter flow H and counter flow C. This is it for every position 1 until 4. Okay, that's it from me. Thank you.
Assalamualaikum. My name is NURYN binti YATIM. Matrix number is B0920100007. So I will continue with discussion number 3. For this question, we need to find LMTD and use the LMTD to calculate heat transfer coefficient for each heated temperature. And then we must comment on how the heated temperature will affect the heat exchanger performance. First, we need to find the LMTD and coefficient for parallel flow and counter flow. This is for parallel flow. Formula for LMTD is TH2 minus TC2 minus TH1 minus TC1 over ln TH2 minus TC2 over TH1 minus TC1. And you just sub in the data and you can get all LMTD for each heater temperature. After you get LMTD, you can find the coefficient, heat transfer coefficient. Formula for coefficient is U equals to QE over A multiplied LMTD. So before we start to find the coefficient, we need to find area of pipe first. So formula for area pipe is pi r squared. After you sub in data to the formula, and you will get area equals to 7.854 times 10 power of negative 5 m squared. And after you get the area, you can sub the area into the formula, and you will get coefficient for each heated temperature. Next, we find the counter flow, LMTD counter flow, LMTD and coefficient for counter flow. Formula LMTD and coefficient still same. Area also same, but different. We use a different data. After you sub the data into the formula, and you will get LMTD and coefficient counter flow for each heated temperature. Next, for next question is how the temperature will affect heat transfer performance, right? So as you can see, stream temperature can vary due to change in the operating procedure. Any alteration in the stream temperature will create a variation in the approach, the exchanger duty, and LMTD, or known as log mean temperature difference. So next question will be presented by Midi. That's all from me. Thank you.
Assalamualaikum and very good evening to Dr. Zahir. I'm MADIHAH FARHANA binti Muhammad FIKRI, number matric BO9201019 from BMMH3553 would present the last question from the discussion, which is the comparison for heat transfer coefficients of two heat exchanger. Okay, this is the table for parallel flow and counter flow. This is the table for coefficient results. Okay, as you can see, for test number 4, it is shown that the parallel flow had higher value of heat transfer coefficient than the counter flow. So basically, the parallel flow is the best heat exchanger of all flows. Assuming that the heat transfer surface and temperature difference remain unchanged, the greater the coefficient value, the greater the heat transfer rate. So in other words, this means that for a certain heat exchanger and product, a higher coefficient value could lead to a shorter batch times and increases the production of the test. Okay, so the last one is the conclusion, which we were required to find 6 conclusion for this lab experiment. So based on the lab experiment, we successfully conducted a parallel flow and a counter flow heat exchanger. On this experiment, we also found on how both of the flow works, and for counter flow, it is known as an arrangement of a heat exchanger where the hot and cold fluid enters at the opposite end and flow to the exit. While for parallel flow, it is known where the hot and cold fluids enter at the same end and flow to the exit. Other than that, we get to show how different cold flow rates affect the performance of the heat exchanger in parallel and counter flow connection. Also making sure that the hot flow rate and heater temperature are fixed. Besides that, we managed to gain the results of temperature, coefficient, efficiency, density, specific heat capacity, and LMTD, also known as log mean temperature and difference, along with analyzing the results and differences from parallel flow and counter flow. Moreover, the purpose of this experiment is to determine the performance test and calculate the heat transfer rate LMTD, and the effectiveness of heat exchanger in parallel and counter flow. So, and lastly, we finally get to determine which flows gives the best heat transfer rate, which is counter flow. Okay, because the counter flow heat exchanger are more efficient than parallel because of a uniform temperature difference between the between the fluids over the whole exchanger and fluid paths. So that's all from our group. Thank you so much for listening.